3D printing in medicine. Module 1, Lesson 1, Introduction to 3D printing. Module 1, Foundations of 3D printing in medicine. Module 2, Additive manufacturing technologies. Module 3, CAD modeling and design principles for 3D printing. Module 4, Slicing and G-code, preparing models for 3D printing. Module 5, Biomedical imaging and segmentation for 3D printing. Module 6, Biomedical imaging and segmentation for 3D printing. Module 7, Applications and future perspectives of 3D printing. Module 8, Practical uses of 3D printing in clinical and surgical applications. Introduction. 3D printing has rapidly evolved from a niche technology into a cornerstone of modern manufacturing. In this lesson, we'll cover the origins of 3D printing, its primary technologies, and how it compares to traditional manufacturing methods. Along the way, we'll also address some of the challenges this groundbreaking technology faces and explore its potential for future innovation. The history of 3D printing. The story of 3D printing began in 1984 when Charles Hull invented stereolithography, SLA. His breakthrough allowed designers and engineers to create tangible models of concepts in record time. With SLA, UV light hardens liquid resin layer by layer, enabling quick iterations that save time and resources. Through the 1990s, new technologies expanded the possibilities of 3D printing. Selective laser sintering, SLS, and fused deposition modeling, FDM, brought diverse materials like thermoplastics into the fold. FDM, which melts and extrudes plastic filaments, became especially popular for functional prototypes and final products. By the 2000s, desktop FDM printers from companies like MakerBot brought 3D printing into homes and schools. Today, advancements such as metal 3D printing allow industries like aerospace to create strong, heat-resistant components, while biomedical researchers use 3D printers to develop tissue scaffolds and even experimental organ structures. This evolution reflects the incredible progress of 3D printing, from its origins to its role in reshaping industries. Classification of 3D printing technologies. 3D printing encompasses several distinct methods, each suited to specific applications. Let's explore the most common ones. 2.1 Fused filament fabrication, FFF. FFF, also known as fused deposition modeling, FDM, is the most accessible type of 3D printing. It works by heating plastic filaments and extruding them through a nozzle to build layers. Advantages: affordable, easy to use, and great for quick prototypes. Cons: limited detail and strength, surfaces may be rough. 2.2 Stereolithography, SLA. SLA uses lasers to cure resin into highly detailed layers, producing smooth finishes ideal for intricate designs. Applications: jewelry, dental work, and other industries where precision is crucial. Drawbacks: resin-based prints can be brittle and require post-processing. 2.3 Selective laser sintering, SLS. SLS uses lasers to fuse powder materials like plastic or metal into durable, functional parts. High durability and excellent for end-use components in aerospace or automotive industries. Limitations: higher cost and slower production times compared to FFF. 2.4 Binder jetting. Binder jetting involves binding powder layers with an adhesive to create models, often in full color. Benefits: fast production and the ability to print complex, colorful designs. Challenges. Parts may require reinforcement for strength. Each method has unique strengths, and the best choice depends on the project's material, detail, and functional needs. Additive manufacturing versus subtractive manufacturing. 3.1 Subtractive manufacturing. Traditional subtractive methods start with a solid block of material, which is gradually carved away to form the final shape. CNC, computer numerical control, machines are commonly used in this process. 3.2 Additive manufacturing. 3D printing builds objects layer by layer, adding only the material needed. Advantages. Reduces waste, creates lightweight structures like lattices, and enables complex designs that are difficult or impossible to achieve with subtractive methods. Disadvantages. Slower than subtractive methods for large-scale production and can struggle with certain material properties. In practice, manufacturers often combine both approaches, balancing the precision of subtractive methods with the flexibility of additive manufacturing. Challenges in 3D printing. While revolutionary, 3D printing faces several challenges. Material limitations. Available materials, such as plastics and metals, have specific properties that may not match traditional materials in strength or durability. Speed and scalability. Printing large quantities or large objects remains slower and more expensive than traditional manufacturing methods. Quality control. Industries like healthcare and aerospace require strict quality standards, which can be difficult to achieve consistently with 3D printing. Researchers are addressing these challenges by developing faster printing technologies, exploring multi-material and sustainable printing, and improving quality assurance methods. The future of 3D printing. Despite its challenges, 3D printing continues to innovate. The development of multi-material printing, self-healing materials, and faster production processes is pushing the boundaries of what's possible. In the coming years, we can expect this technology to expand into new industries and applications, transforming how we design, manufacture, and live. Conclusion. 3D printing has come a long way since its inception, evolving into a versatile tool for industries ranging from healthcare to aerospace. By understanding its history, methods, and challenges, we can appreciate how additive manufacturing continues to revolutionize the way we create and innovate.